Section 3.1, Algorithms. An algorithm is a finite sequence of instructions for performing a computation or solving a problem. So in the past, a simple formula might have been enough to arrive at our answer, but now we're getting to problems that are more complicated. They require a procedure, as this says, a series of steps to get us to the solution. So let's take a look at a really simple algorithm. So say we're asked to find the maximum element in a sequence of numbers. So I've written this algorithm in really generic pseudocode, right? But it includes all of the steps required to complete the problem. There's no complicated logical step that is missing here. So the first thing I do if I'm looking for the maximum is I assume the first element is the maximum. Then I'm going to walk down the list. If I find something larger than the current item I've identified as the maximum, assign the maximum variable to that element. Then return the maximum at the end of that sequence. So if I want to run the algorithm on the list of numbers 3, 2, 5, 4, 7, 3, 1, this is how I'm going to trace what's happening with the algorithm. So the for loop starts there. It starts at 2 and it runs until n. So that's just shorthand to say that I'm doing a for loop from I equal 2 all the way through n. So when this loop starts, I will be set equal to 2. The maximum element is a 3 at the start of this for loop. And AI, the second thing in the list that I am looking at, is a 2. I compare those two, no change, moving into the next step of the for loop. So the next pass of that for loop. I increments up, right? The generic I++ here. So I would go to 3. The max element is still a 3 because we didn't change it on that last pass through the loop. However, the third element in the list is a 5. So AI, the current element I'm looking at, is a 5. So swap out the maximum element. And we keep running through the algorithm. And we find a 7. So we return a 7. It's important that you be able to trace this code. I can occasionally ask you, here's a block of code, trace and see what happens to it. A searching problem is to find an element X in a list of distinct elements, A1 through AN, or determine that's not on the list. So we have a couple list algorithms we want to go through. These are all really basic problems. You may have seen these before in your computer science courses, but the idea is that we want to look at, hey, here's a problem, find something in a list. And even though that seems really simple, there's actually a bunch of different ways you can go about that. And that's why it's useful to look at the number of a number of distinct algorithms. Say, hey, look, this really simple problem can in fact be broken down in different logical ways to solve it. Perhaps the most straightforward is just the linear search. This code is essentially the same as our max element algorithm, only now I'm just walking down the list saying, hey, are you the thing I'm looking for? Are you the thing I'm looking for? Note the declaration step here. I say I have a procedure. It's called linear search. X is an integer. You need to give me that. You need to tell me what I'm looking for. You need to give me A1 through AN. Those are distinct integers. You need to tell me what it is I am looking for. This one is a little there's a little bit of efficiencies coded into it. It has that return statement in the for loop, exiting out of the for loop when we find it. In particular, note that this returns a 0 if we have not found the element, and my list starts increment at 1. A sub 1 is the first distinct integer in the list that I could be looking for. So let's see what happens when we do the linear search we're looking for an x equals 7, and we're looking for it in the list 3, 2, 5, 4, 7, 9, 1. I'm going to trace it similar to last time. When the loop increment starts, I set equal to 1. The first element I look at is 3. That's not it. Keep going. When the loop increment goes to 2, I look at the second element. That's also a 2, but that's not the 7 I'm after. Look at the third, the fourth, the fifth. The fifth element, I've spotted it. It's the number 7. So I'm going to return 5 because I found it in position 5. Let's do the same thing. We have the same list. We're going to run the same algorithm, but now I'm looking for 8. Only here, it runs all the way through, does not find an 8. It exits the for loop and returns a 0 because the 7 is not found. A really, really powerful search algorithm is binary search. Now, the crucial change here is that I'm assuming the list has been sorted. So the description is to compare X, the thing I'm after, to the middle element in the list. I call it A sub M. If X is greater than A sub M, then search the upper half. I'm sorry, typo right there. It should be A sub M. Search the upper half of the list. Otherwise, search the lower half of the list. And I'm going to keep repeating this list until it's reduced to a single element. So what you're going to see in a second when we trace this is what's going to happen is I'm going to keep cutting it in half. That's going to turn out to be really powerful and really fast. So I have this big long list of numbers. I want to try and find the number 8. So at the first pass, there are 16 elements to look through. So I'm going to take them and separate them out into 2 halves, the lower and the upper half. There are some decisions to make, some particulars you have to decide when you're coming with the algorithm. We're going, as these lists are evenly split, we're going to let AEM be the maximum element in the lower list. So in our code here, as we'll see in a second, AM will be equal to the element 10 in the list we are searching through. So I compare 8, that's the thing we're looking for, to the 10, and I determine, oh, what I'm looking for must be in the lower half. So now I just kind of push the upper half to the side. Don't need it anymore. I know it's somewhere in the bottom half of the data. So I'm going to repeat the exact same process I just did, only on half the data, because I know it's in the bottom half. So I cut it down in one step. I cut it down from 16 to 8. Again, I split this list in half. I look at A sub M, which in this case will be the 5. I compare, 8's greater than 5, so now I know it's in the upper half. Got 4 elements now, split it up, 2 and 2. Compare the 8 to 7. Oh, it's still in the upper half. Keep going. This time when I look at it, I compare 8 to 8, and I say, well, X is less than or equal to 8. So I'm going to repeat the process on the lower half of the list. Now this is these are the most simplistic versions of these algorithms. This is where you could code something to shave off some time here. However, that does put us in the single element case, so we found it. Here is what that code looks like for the process we just did. So note, ours assigns M to the floor of I plus J over 2, right? We kept going with the maximum element in the lower half of the list. This is where you could change it. You could pick the lowest element in the upper half of the list, that kind of stuff. These are all choices that we'll talk more about the efficiency of algorithms in later sections, but these are all choices that don't really change. They won't change the overall efficiency of the algorithm. Now, it turns out that this code is a little harder to trace, so I want to go over an example. Now that we have a feel for how the algorithm is supposed to work, let's trace this code as it does do its work. So I know that I and j are going to be assigned to the top and the bottom of the list of numbers. So in the first pass, I is set to 1, j is set to element 22. Note that's in position 1 and position 16 respectively. And m goes to I plus j over 2 floor function. So it's going to be looking at element 8. AM, then, the element at position 8 is a 10. So I'll look at the lower half, reassigning j. So j gets reassigned to AM, and AM gets recalculated, in this case, to position 4. Run it again. This time, since it's in the upper half, I gets reassigned to element 5. And I keep running this, and we can see how I and j are collapsing in together until they are pointing at a single element. That element either is the thing we're looking for, and we conclude, hey, we found it, or it's not the thing we're looking for, and we can conclude it wasn't on the list. In this case, we're looking at the same data set. We found it. It's in the 7th position, so we report back a 7. Another really common type of algorithm and really large problem that we need to tackle in computer science is sorting. So it's one of the most common problems. There's a lot of different ways to go about doing a sort. And because it's such a fundamental problem and your computer spends so long just sorting all the time, um, it is a problem where there's over 100 different ways to 100 different algorithms for just sorting. And that sounds silly, but this is just a problem that is so crucial to so many of the operations that your computer wants to do that coming up with the best way to sort is just a crucial problem. So we're going to go over a couple here, some really basic ones. And one we're going to start off with is bubble sort. So bubble sort's this nifty idea where you just start successively comparing elements that are standing by each other. So the first time you pass through, you'll compare the first and the second. And if they're not in order, you swap them. Then you compare the second and the third. Note that the swap may have already happened. So what will happen as you do this, that first pass, is the largest element will bubble up to the top. Here's a little GIF of it being ran. It's a slightly more sophisticated version. But you'll notice what happens is it compares and the elements swap out. And on that first pass, the largest element bubbles all the way to the top. So then once we can guarantee that the biggest element has bubbled its way to the top, the next pass, we don't need to do a comparison between the last element and the second to the last element. So with each pass, we get to knock off one comparison. So let's see this in action with the list 5, 3, 1, 2, 4. So I have my list here, and the first thing I'm going to do is compare the first and second element. I'll be using this red filled in double arrow when I want to swap. So 5 and 3, 5 is not in the right position, so swap the two. So now this is the list I have, 3, 5, 1, 2, 4. Compare the second element and the third element. That's 1 and 5, swap. Compare 5 and 2, swap. Compare 5 and 4, swap. So now going into the next pass, I will have 5 has bubbled all the way to the end of the list. The maximum element is in the correct position. So this is what the second pass looks like. Note, as the list is small and we can absorb it all at once, we know that 4 should be bubbling its way to the second to the top position, second to last. We can see here the final comparison. I didn't fill in the comparison 3 and 4 because I compared them, but I'm not going to swap them. Pass 3, no swaps. Pass 4, no swap. This is an example. We're going to go through a really basic version of bubble sort, but you can see here that pass 3 has no swaps. So we already know pass 4 has no swaps. So you can actually, again, make this bubble sort a little more sophisticated and say, hey, if I ever make a pass with no swaps, go ahead and exit out. But we're going to be looking at the most basic pseudocode for this algorithm. Now, you'll note that here, I cut a few corners saying swap AJ and AJ plus 1. Depending on the language you're using, there may not be code for that, but we know that you take one of those elements out, store it in another variable, and then move it back. But I'm just using shorthand there because I feel like it's not skipping any complicated logical step that might be tricky. Do note that I have a nested for loop there. The first for loop does the number of passes. The second for loop does the comparisons. Now I know what you're thinking. I was claiming there are all these ways to sort. Give me at least another one of them. Well, here's insertion sort. So what it does is it says the first element, you're sorted. You're where you're supposed to be. Then it grabs the second element and it takes it in the list where it should go and puts it in. So it kind of has this demarcation. Here's the sorted part of the list. Here's the unsorted part of the list, and it grabs one element at a time, holds its hand, and places it into the list where it belongs. So during the jth pass, a sub j, the jth element, is placed in the correct position among the previously sorted j minus 1 elements. So let's see this one in action. How are we going to trace this? Say I'm trying to sort that same list, 5, 3, 1, 2, 4. At the first pass, I assume that the first element is sorted. Pass 2, I grab an unsorted element, 3, and place it where it belongs in the sorted list. Next, I grab 1, and I place it where it belongs in the sorted list. Grab 2, place it where it belongs. And grab 4 and place it where it belongs. One way to kind of imagine these algorithms, and it can be really helpful, is at a fundamental level. You may think, well, he's just coding them slightly differently. It's doing the same operation. But the question is, how much work do you have to do? So if I'm trying to get, say this is an in-person class and you guys turn in your exams and I drop them. And now I'm trying to get them all back in alphabetical order. Do I do bubble? Do I lay them all out and I just kind of bubble the top one to the top of the list? Do I say, here's a new exam, and do I put it in alphabetical order, inserting it into the pile where it goes? These are fundamentally different approaches to the problem. Here's the code for insertion sort. The major for loop there is the one running the number of passes, right? We know how many passes it's got to run because I have to take each of the unsorted elements 2 through n and place them in the sorted list. This block of code right here, essentially the while loop, finds the correct position. And this really lengthy code here is the part that I just said, hey, swap. It's not complicated code, but now I got to move all the elements around. There's a category of problems called optimization problems. And with an optimization problem, I'm trying to min-max, right? I'm trying to minimize something or maximize some criteria. This is a broad category of problems, right? If you're trying to eat lunch, you're trying to maximize the value that you can get with the money you have in your pocket. But what are the criteria, right? Do you want quantity? Do you want quality? Do you value how close it is, right? So you're trying to optimize based on whatever criteria you establish. One solution, one way to find solutions to optimization problems are what's called greedy algorithms. So it's important that you note that both of these are broad categories. Optimization problems come in many shapes and formats, and greedy algorithms is one generic type of approach. So this is an algorithm that makes what appears to be the best choice at each step, based again on some criteria. So we're going to look at one such greedy problem. We'll actually end up looking at two. Let's start with this one, the change making problem. So say you want to make n cents of change using as few coins as possible. So the greedy algorithm, right, it's not looking ahead, it's looking at the right now. And so the greedy algorithm for change making, we can establish criteria and say, hey, this is our algorithm. We're going to, at each iteration, use the coin of largest denomination that does not cause the total to exceed the change we owe that person. So say we want to make change for 42 cents, right? We're in some world where we're not, or the cash register opens and we have to give actual change out to the person. What do? 42 cents is owed, you grab a quarter. Well, now you still owe that person 17 cents, but you can't give them a quarter anymore. That'd be giving them too much. So you move down the list. Can they take a dime? Yes, they can. Now you owe them 7 cents. No more dimes because they are not owed more than 10 cents. So you give them a nickel. No more nickels. Give a penny. Give a penny. So the end result here is 1 quarter, 1 quarter, 1 dime, 1 nickel, and 2 pennies. So note that that is a total of 5 coins to give 42 cents. Here's the pseudocode for that. Again, nothing real special happening. Just make sure you walk down that denomination. Note that this code is working for any denominations that you give in decreasing order, not just US coinage. So here's the theorem. The greedy algorithm for change making makes change using as few possible quarters, dimes, nickels, and pennies. So we're not going to prove that, but what I will say is that it may not be optimal for other sets of coins, which is an important takeaway right here. So the greedy algorithm, you kind of think of it as being short-sighted. We'll talk more about that in a second. But say the cash register opens and you don't have any nickels. Well, now if you apply the greedy algorithm to the 42 cents, you'll give a quarter, a dime, and 7 pennies. So you'll have to hand over 9 total coins. But the optimal solution is 4 dimes, 2 pennies. And that's the sort of thing that our brains are so amazing, you probably came up with that in no time. But how do you tell a computer, how do you write the algorithm that says this is how I came up with that solution? Let's look at another example. Let's say we want to schedule some talks. So we only have 1 room available, and we have a bunch of people that are trying to schedule talks in that room. At most, 1 talk can be scheduled in the lecture hall, right? We can't be double booking it. And we want to schedule as many talks as possible. Now we're going to be looking at 1 example, but keep in mind this could scale up. So let's apply a greedy algorithm to it, right? That seems like a good solution here. So at each iteration, we're going to take the earliest end time, right? Maybe if we get people in the lecture hall as soon as possible, we'll be able to pack the schedule that way. So here's our possible list of talks we can schedule. So using start time, we schedule 2 talks. Talk 1 has the early start time, so we schedule it. Then we're looking around. The next talk we could fit in, right? By scheduling talk 1, we lock out 2, 3, and 4 because they all start before 1 ends. So we have to schedule talk 5, 2 total talks. Well, that's not good enough, you say. So you go back to the drawing board. Why don't we, instead of scheduling with a starting time, pick the shortest talks? That's got to work, right? So with this method, we'll schedule talk 3 first because it's only an hour long. And then you might have set up some secondary criteria. But it turns out, due to the overlapping nature of the talks, talk 5 is the only other one we can schedule. So it didn't change anything, right? We got a different answer, but we still only scheduled 2 total talks. And that seemed like really good criteria too. So it's important to note that both of these seemed like logical next steps. Let's try one more greedy criteria. Let's try and use the ending time. So the ending time we will end up scheduling, so this is where we choose the earliest end time, we'll schedule 2, 4, and 5. So there we got 3 talks. And it just turns out if you look around and try this out, using starting time, not optimal. Using shortest duration, not optimal. Using ending time is optimal. And all 3 of these are greedy algorithms. And again, it shows that we're not guaranteed to get an optimal solution just because we're using a greedy algorithm. So then why do it, right? Why apply a greedy algorithm if it's not going to be optimal? Well, think about scheduling all the classes on campus. That's a huge problem. We'll learn more about the growth rates of these problems and how these algorithms are efficient. But we can't run through every single possibility. When it's only 5 talks, yeah, we could just write down all the possible combinations and pick the optimal one. The good thing about a greedy algorithm is it arrives at a solution, right? It uses the criteria, it makes the decision with what's best at hand. Here is our code for writing greedy algorithms, or sorry, scheduling talks using a greedy algorithm. Here, this is the one that's going to sort the talks by ending times. So again, one thing to call out here, the theorem a greedy algorithm will always find an optimal solution is wrong. But lots of things use greedy algorithms anyways, because given that we don't have an infinite amount of computational power or time to work on a problem, a greedy algorithm may be the best that we have. Lots of things in nature, right? If you have ants building their colonies, they're using a greedy algorithm to do that. So it's not like they don't arrive at optimal solutions. It's just not guaranteed that we will arrive at an optimal solution. The other go-to that I always use is, say that we're trying to move, right? I call you over to my house. I'm like, hey, I got to pack up my house. How are we going to start to pack the truck, the moving truck? We're going to apply a greedy algorithm, right? We're going to take the biggest items first and put them in the truck under the assumption that that will fit in the most items or fill in the most volume, right? If you're packing for a vacation, you might do the same thing, right? Only there, your greedy algorithm might be slightly different. Maybe you have a value assigned to each item, right? My laptop is super important, and then I need this item. And so you're going to start packing it with a greedy algorithm based on the importance of the items. That doesn't necessarily mean you'll get the most value out of packing it in that order.